So, welcome everybody from my side to our today's session. I would like to start with an overview and schematic overview of a typical power module. As you can see, we have semiconductor dies, and we have, of course, substrate material, DCB, AMB, or material, which consists of copper in the ceramic insulator, and of course a cooler. And all these components have to be joined together. So we have a die attach, we have a top side contact, we have a large area contact, we have wire bonds for the gate, and also maybe wire bonds for the current, but not only wire bonds, also ribbon bonds, clips, and also then for the AC contacts here, we have, for example, laser joints or ultrasonic joints. All these technologies are then used in various forms of power packages. Here you can see a IGBT module with its typical form, the wire bonds. It's typically then encapsulated by potting a silicone as in order to have an electrical insulation. All these technologies are also used in double-sided power modules where you have a double-side contact as shown here, which is from a BMBF funded project, Ultimo was the name. And we have also here the possibility to embed the silicon carbide dies in a printed circuit board. This is also a technology we have here in-house. And then you can build such modules like you can see the cross-section here, or here, which is a picture of also a BMBF funded project where we also embedded here the dies in a printed circuit board. And we have not least the possibility to use molded modules where we use the transfer molding technology, which is also something we have here at IZM. I would like to talk today about some of the very important metallic interconnection technologies. So most important is, of course, the tin silver copper soldering, or some other slightly modified alloys which are used for die attach and also for large interconnects. Of course, what is also very much in use today is the silver sintering. Copper sintering is coming up a little bit now, and we are investigating this also as a future technology. We will see if it replaces the silver sintering somehow. Of course, we could also use gold or the gold-rich solders, but these are more used for applications where costs don't play such a big role. And we have also a technology which we call transient liquid phase bonding or soldering, which others call solid liquid interdiffusion or diffusion bonding, where we use the special property of the tin copper system to form intermetallic phases. Let me go further here, and let's begin with the solder joints. The most important thing with the solder joints for power electronics is that the solder joints have to be more or less voidless. So we have to have processes where we get rid of all the voids or don't form voids in the first place. So we have three different kinds of soldering. So we have the convection soldering, where we heat everything using a hot gas or air. We have the condensation soldering, where we use an inert medium which condensates on the power module and transfers the heat then to the module. And we can also use a hot plate, a conduction soldering, in order to form a die-attached solder joint or a large area solder joint. The special thing is if you use a conduction soldering, you can, if you don't use any form of liquid flux which can evaporate and be entrapped, you might be able to circumvent the usage of vacuum, but in most cases, vacuum is part of the process in order to get rid of the pores to and at the end achieve almost voidless solder interconnect. Here you can see a microstructure of a tin silver copper solder. For power electronics, we also use, there's also the usage of tin silver copper antimony solder, for example, in order to have a higher strength and a higher melting temperature, so that the lifetime can a little bit increased. Yeah, here you see again a picture from the SiC module picture from the BMBF project. And here you can see a IGBT die, which is soldered on a DCB substrate. The transient liquid phase bonding is also a sort of, let's say, soldering, because it's more or less a solder joint, but the special thing is that the tin is totally transformed, or at least almost totally transformed, into intermetallic phases. You can either use paste, where copper particles are in the paste, or you can use galvanic layers. You see very thin layers. You put it on, in this case, on a copper lead frame or also a DCB substrate, AMB substrate. And then, because everything is very small, so the gap is very small, we have a very thin solder line. Already during the soldering, everything transforms into intermetallic phases. You'll see this is 1 micrometer. It's only a few micrometers thick then. The good thing is you have then achieved a higher remelting point of more than 400 degrees Celsius. So you are beyond this line here, 415 degrees C. You have a higher creep resistance, and you may achieve higher lifetimes, but you have to be careful, because solder normally accommodates the thermomechanical stresses, and this is not possible with intermetallic phases, because they cannot plastically deform. They are more or less brittle. So you have also always bear in mind that if you use the transient liquid phase bonding or soldering, you need to have another material, or you have to somehow allow the system to bend and to accommodate the thermomechanical stresses elsewhere. The silver sintering is somewhere between the normal solder joints and the transient liquid phase bonded joints, because it's ductile. You can see that here on a micro scale. If you do a tensile test of such a material, you see that you have plastic deformation here on a micro scale. Of course, if you make a tensile test of a porous material, you macroscopically get a brittle fracture, but it's not the same as with ceramic materials. If you look at the microscale, you see that it's, of course, because silver is a plastic deformable material, you see these plastic deformations. So it can accommodate stresses, but the creep resistance is much higher than that of solder. and therefore it is very promising for higher lifetimes. And you see, you can adjust the micro porosity by just simply apply different forces during the sinter process. So if you do it without any pressure, you get you receive such a quite high porosity, and the higher the force is you apply during sintering, the lower is the porosity. Here in this case, it's lower than 10%. In order to qualify such joints, we have, of course, destructive methods, but it's not so simple because of the large area to do shear testing, though one of the first things you can do is just use a bending test, and you see if it looks like this, the quality was not so good. Of course, we can use FIP cuts in order to see the interfaces here and also the porosity. And very important, of course, is besides the X-ray, where you can see defects like voids, the acoustic microscopy, where you can see two-dimensional defects, like for example, delaminations, as you can see it here, which could not be seen in an X-ray photograph itself. So these two look the same, but the quality is really different. This is a high quality, and this is very poor quality. Of course, cross sections are also very important because the focus ion beam method is quite expensive, and it is only applicable on a very tiny scale. It's not so easy to prepare these samples. You need to be you need to apply proper preparation methods, and if you do so, you can really reveal the microstructure, the porosity, the interfaces. Here you can see the interface on the die side, so the silver with a direct interconnect to the die metallization. And here on the substrate side, you see interdiffusions shown here. You see that the gold partly really diffused into this, the silver here. Yeah. It's very very important to have these means in place in order to assure the high quality of the silver interconnects. Yes, you can also use the silver sintering for large areas. So this is also more or less state of the art to use silver sintering for the interconnects of the substrate to the cooler. You see, we have here carried out some reliability tests, and you see that even after 1,000 cycles passively tested, you see that we have only a very small amount of the area here deteriorated. The crack propagated from the corner a very short distance inside. So this would be totally different if you compare it to ordinary solder joint, which we have done, which is not shown here. Yeah. What is really important, not only for soldering, this is an example for a solder pad, but also for sintering, is that the surfaces are clean. And what we use is that we see some problems, or we would like to really be sure that our surfaces are clean. For this purpose, we use the XPS analysis method. So we have an X-ray which bombards the surface, and the photoelectrons which are then detected are ejected here. And then you can really see whether your surface is, like in this case, is contaminated with nickel. It should be pure gold and not nickel on the surface. And what you can also see is the chemical nature of the nickel. In this case, you see that it's not a pure nickel, but it's a nickel hydroxide or nickel oxide. So this is very unique with this XPS surface analysis tool. And the information depth is only a few nanometers, around 10 nanometers. So you get really information of the surface and not of deeper layers. You can also use it, as already mentioned, for the silver sintering. This is an example where we sintered on a thick film silver platinum metallization on a ceramic. This is normally done together with the thick film application with a sort of glass. And you see that in this case, some elements of the glass are really found on the surface. And these glass contaminations on the surface prevented us from getting a proper joint. You see a gap has formed here, and we can really then see it in the XPS spectrum that we have lead. So it's really lead oxide, which is in the glass. We have here some other elements. And if we then do, which is also done in the XPS analysis tool, back sputtering using argon ions. We see after doing this at 5 kilovolts for 300 seconds, where we don't exactly know how much we back sputter, but let's assume 20 nanometer, 50 nanometer, we see that these contaminations are gone. So we know this was really something which was more or less somehow a contamination on the surface of the silver platinum thick film metallization. Of course, all these surface analysis tools are also important for any of our interconnection technologies. And I would like to now come to the next ones, which is the wire bonding and laser bonding, and also the ultrasonic welding. So the wire bonding, of course, the thin film wire bonding is not so much in use for power modules, but of course for all the printed circuit board assemblies which are around the power module. And for the power module itself, we need heavy ribbon bonding, we need heavy wire bonding. For the terminal contacts, for the high currents, we need either ultrasonic welding, or what we also use is laser bonding, which is a quite new technology, but it's very promising. You can see here copper and copper welded by a laser. So you have also a monometallic interconnect, which promises a very high reliability then. Here are some more examples of wire materials. Of course, copper wire is used, but you need a larger, thicker copper metallization then on top. Otherwise, you destroy the die. For this purpose, also copper aluminum wires were introduced, where you can see that after bonding, you have a plastic deformation only of the aluminum, and the copper core stays more or less undeformed. And then in operation, it can carry the high currents and also gives more strength to the whole system. What we also do here is that we do active power cycling of our wires, and you can see here two wire materials in comparison. This is a aluminum scandium wire after active power cycling, and this is a pure aluminum wire. You can see here the crack propagation, and you see also that there are differences in the crack propagation. It's a little bit closer to the die with the aluminum scandium wire. And these are all interesting results here from these special materials. Of course, we have also here ribbons in place on power modules, which are more or less state of the art. These power cycling tests can be done for whole power modules as a standard test. It can be done for ribbons or wires, as has been shown on the last slide, or we can also do it with a special focus on the die attach, as you can see here. We have here the IGBT die, which is used here as a heater, so we don't use the full current, so we use it in a state where it's normally not used. So in this state, it is sufficient to use only very small wires, so that these wires are not don't fail during the test. This is very important. Otherwise, we could not really finalize the test. And using this very special setup, also with a constant delta T instead of constant current, we can then really compare different die attach technologies. And in this case, we did this comparison with tin silver solder, which failed after 40,000 cycles. Much better already was the silver sintering without using pressure. This was at around 400,000, so it's a factor of 10 already. And if you, instead of using no pressure during sintering, use a higher pressure of 5, or in this case 30 megapascal, you can achieve another factor of 10 in lifetime. So you see, if you compare the pressure sintered joints with the tin silver joints, you have a factor of 100 between the lifetime. And with this special test setup, even the copper tin transient liquid phase bonds survived even more on average, but we only tested 3 samples, so it's more or less in the same range as pressure sintered joints. And here you can see the test setup. We have, of course, to calibrate the temperature, because we really use a constant temperature. So if we go to higher temperatures, then we have a premature failure, and we could not really see then also the failure mechanisms. You see how these joints fail. You see, because it's active power cycling, the joints fail more or less in the middle, but it's not so far away from what you really see if you look at power modules in the field, because also there they are more or less under active power cycling. With this reliability test results, I would like to finish my talk for today. If you have questions concerning processes, failure analysis, analytics and quality tests or reliability tests, you can ask us anytime. This is what we offer. I do not want to go into more detail now. We would be glad to hear from you, and many thanks for your attention.